Thanks for joining today's webinar. We're going to focus today on validation and characterization workflows that are simplified by the 5 Series B MSO. My name is Brandon Gould, and I'm really excited to be here with you today. We're going to jump out of these slides almost right away and get into a demo where we're going to cover the user interface that was designed for this oscilloscope to be optimized for touchscreen interaction, so it kind of works like a phone or a tablet. We're going to focus on the hardware that was designed for best-in-class signal fidelity, as well as some of the probes that Tektronix has designed and brought to market with patents for connecting to the device that you're trying to actually test. We'll do one overview demo where we kind of go over all of that at a really high level, and then we'll dive into very specific use cases. We're going to look at embedded design, so like chip-to-chip communications with some serial decodes and some simple measurements. Wide bandgap, which is silicon carbide and gallium nitride testing. Fast switching devices with lots of power, lots of voltage and current. We'll then transition over to inverter and motor drive testing, things that have three-phase power in them. And then we'll cover briefly a few innovations around cloud storage of your measurement results, screenshots, etc., as well as remote collaboration. As you can tell, I'm here in the home office, so that kind of remote collaboration is really important for myself, as well as for engineers across the world as we're living in this new norm with COVID. Throughout all these demos and all these slides, I'm going to highlight three major themes. The first being simplicity, the second being accuracy, and the third being speed. So simplicity, accuracy, and speed are going to be highlighted throughout. I'm really excited, so let's jump in. One thing on the logistics. Throughout the session, if you have any questions, please drop them in chat, or there's a questions tab here right below the webinar video, and our team will be sure to follow up and get back to you with answers. So at Tektronix, our vision is that we are the essential technology for the people who accelerate progress. And those people who are accelerating progress, that's you, right? You're the design engineers, the validation teams, and the inventors who are making an impact in healthcare, EV and battery efficiency, data centers, aerospace defense, and across all industries that need electronics to function correctly. And at Tech, we are here to help you bring up and debug new designs, scale up your teams during periods of rapid growth, and give you the support that's needed when issues come up. And we really want you to be prepared for the unknowns of whatever that next project is that's going to land in your lab. Ultimately, we know that you want to focus on what it is that you're working on, right? Your NPI or your program, your science experiment. And you don't really want to spend hours and days understanding the complexities of the test and measurement equipment that is needed to be successful. You really want to focus on meeting your timelines and quality expectations. Right? You kind of want you want your test and measurement to get out of the way so you can focus on what you're doing. So here is an image of the 5 Series B MSO. We've had our this platform of scopes out in the market for a couple of years, and here's what customers are saying. The biggest thing for us was the user interface and how intuitive it is and easy to learn. Everything just made sense. Having 8 inputs has been a real game changer. I've never been able to see this much without trying to connect 2 scopes. When we bought the scope, we knew it would meet our needs for years to come. It's got everything we need and more. We'll talk about that today. That's kind of like future upgradability. You can add capabilities as needed down in the future. And it's never been easier to collaborate with colleagues than it is with TekDrive and TekScope. I can do almost everything from my computer at home. We'll touch on that at the end here. And my team's gotten comfortable with this user interface, and it's nice to have higher performance and lower cost options under the same UI. This is from a lab that's using some of our 4 series oscilloscopes, so that is a lower price option with a little bit lower performance. We're talking today about the 5 Series B MSO, kind of in the middle of this platform. And we also have the 6 Series B MSO, which goes up to higher bandwidths, higher sample rates, and higher memory lengths. So let's do a quick agenda overview. We're going to be packed full of demos here today. And these 5 demos are going to be on, first off, an oscilloscope that's easy to use. That's going to be a general user interface and an introduction to the oscilloscope. Second is going to be embedded design, so chip-to-chip communications and embedded design, some serial decodes in there. Third, we'll look at switching analysis, either traditional silicon or wide bandgap. We have some double pulse tests and other high-speed switching applications on here that make that kind of characterization and validation a breeze. We'll then look at three-phase inverters, motors, and drives, and then lastly, remote calibration, so cloud and PC-based workflows. Again, we're going to focus on talking about simplicity, accuracy, and speed, letting Tektronix get out of the way and having confidence in our data, our decisions, and the recommendations that we make with our designs. So you're probably working on something that looks like this, right? You have some kind of a circuit board. Maybe you're trying to bring microcontrollers into a system and you're debugging issues on your microcontrollers. Maybe instead of what's shown in this image, maybe it's more that you're working on some switching FETs, some MOSFETs. But whatever it is, this is kind of the image of that we view of what you're doing. You are interested in buying an oscilloscope. You're not exactly sure which one to get right now. You definitely are going to need some probes. So inside of our platform, we have 25 years of probing innovation with tons of patents. More than 80 patents in the last 25 years of our innovations in probes, current probes, voltage probes, power rail, a whole portfolio of fantastic probes. Recent innovation has been on the software side, so automating your measurements, making sure that you have confidence in the way that things are being calculated and measured, so that you're not manually setting up tests, sharing data quickly and turning that data into insights. Getting rid of USB sticks, email attachments, and having a nice to easy to collaborate area on the cloud. And we're the ones who designed the scope. We're the ones who built the scope. Our engineers know all of the tidbits about what's going on inside the scope. So, we would love to be honored to be the ones who are calibrating and repairing your equipment when needed and protecting your uptime in your labs. So this is all kind of centered around your application. This is a flexible platform, flexible hardware, software, probes, and service offerings to make sure that, again, you can focus on your project, your deadlines, your quality expectations, and not on your test and measurement solution. Again, here's some of the applications that we're going to talk about today. So on the top left, we've got converters. This could be AC to AC, like charging stations for EVs. This could be AC to DC, like onboard chargers, something like in your laptop. DC to DC, onboard converters, power rail conversion. Embedded systems is another area where we're going to focus today. Wide bandgap, like we talked about. Motors and drives. This here's a BLDC motor. Basically any kind of a three-phase power, we have a solution around. Frequency response, this is doing Bode plots and looking at how a frequency input impacts the circuit. And then switching analysis, this is a double pulse test set up with a source measure unit, a DSC power supply, arbitrary function generator, and an oscilloscope looking at how this silicon is responding to inputs. First off, let's do that general product demonstration that I talked about. So here we're going to learn about how to turn channels on and off, do measurements, add callouts, what happens when we attach different probes, and we're just going to get comfortable with the user interface here of this 5 Series B MSO. Okay, first off, let's familiarize ourselves with the user interface here. So in the middle, we have our waveform. This looks like some sort of a clock. Down in the bottom left, we have our channel 1 badge, is what we call this. A single tap lets you change the vertical settings. A double tap lets us look even greater in depth, so we can set labels, set offsets, vertical scale, position. We can compensate our probe. We can turn on this feature called Spectrum View, which replaces FFT. And then in other, these are some of our advanced setup, like D-skew, alternate attenuation, alternate units. If this was some kind of like a Rogowski coil, you could put a scale factor and have this show up as current rather than voltage. Down in the bottom, this is how we can turn channels off and on, right? So you tap 2, on comes 2. I have this set up right now as a remote connection, but I could just tap this 2 and swipe down. and it would delete channel 2. So you can see here I'm using the mouse and the keyboard, but even easier would be things like a pinch and zoom. This is how you can change the horizontal scale, a vertical scale, a pinch and a drag. So yeah, let's turn on channel 2 here, and we can see right here we get a warning that there's clipping because I haven't yet optimized this signal and set the vertical scale and the vertical offset. Then we have our math waveform, so a single tap. This by default will just start with a channel 1 minus a channel 2, but we got the standard addition, subtraction, multiplication, division. We can add filters. We can do advanced math, where we have an equation editor. We can add a reference. So this could be something that's been saved off from another oscilloscope, a golden waveform, something to compare to. We can add a new bus. This is for when we're going to focus on this in the next video or the next demonstration on embedded designs. We have a digital voltmeter and an arbitrary function generator that has up to 100 megahertz sine wave and a whole bunch of different functions, as well as you can have this turned either off like now, continuous, where it continuously cycles the same sine wave, square, sawtooth, or burst. Let's say you wanted to just do 2 pulses or 10 pulses or 20 cycles. You just tap this button right here and it turns on for however many cycles and then turns back off. Horizontal, these are our horizontal acquisition settings. Again, a single tap shows you at a quick glance how to change the horizontal scale. A double tap lets you do things like get into the manual horizontal mode where you can control sample rate, record length automatically. Over here in trigger, we have a bunch of advanced trigger types that work on all of the inputs. Here I have a logic probe connected to channel 3. Let's look at what that looks like. So channel 3 I've turned on. We're going to change our horizontal scale so that this makes a little bit more sense. Let's go ahead and stop that. So you can see here with the logic probe, when I plug the logic probe in, the oscilloscope automatically goes over from this analog input to these 8 digital inputs. Just does that automatically for you. And in here you can see that we can set thresholds for all of those 8 different inputs. And over on the trigger, we'd be able to trigger on any of those, like if you were to trigger on D4, right? Here we go. Now I got a really stable trigger there on D4. Let's go back to triggering on edge on channel 1. In acquisition, this is where we can do things like enable our history mode, fast frame. We can do peak detect, average, set up a single acquisition. And then in the top right, this is where our measurement engine. So this right wedge that we have right here, this is our measurement readout area. So we're going to have some badges show up here. But let's say that we just need a visual clue. We can slide this over and we can maximize the screen for what's happening to our signals. Or we can open this up and we can do something like, let's turn off that digital input. Right click, we can turn off. Let's add a measurement here. So I'm just going to drag and drop that on channel 1. And let's say that we want to do something like a frequency measurement. Here we go, 40 megahertz. And it looks exactly like it's 40, but let's learn about that. Is it really 40 megahertz perfectly every time? I turn on the advanced statistics and now we can see what the average is, the standard deviation. The maximum was 55, the minimum was 35. And that's great and all, but I'm a visual person, so I would like to see what does this distribution really look like. This 40 megahertz clock, let's do a histogram. So we have a really nice, neat distribution. It looks, kind of like normally distributed over 40 megahertz, and a couple, it looks like probably outliers up here at 55 megahertz and 35, because I see that those happened, but I don't really see a distribution that evens out in there. So just a couple of taps, we can really understand. I've got some kind of a glitch happening here on this clock here. So we've gone over channels and measurements, a little bit on probes. One thing I said we'd cover is callouts. Let's just maybe finish going through this add new. So we've added a measurement. We can add a results table here too. Like right now we have a measurement up, so we can add this results table, which shows the same advanced statistics that are in the badge. I am wasting a ton of space on my screen right now with all of these blank rows, right? So let's reorder things so that we're not wasting so much space. Everything is really easy to reconfigure and move around, as you've seen there, right? We can get things set up pretty much however we want. That's the result table. Callouts, this is where we can add notes. So I can double tap to edit this. In here we can type anything, right? This is a callout. And in formatting, we can make this match. These are the channel colors. So channel 1, 2, 3, 4, 5, 6, 7, 8, if you want things to match your inputs because you're saying something about that specific input, or any of the other colors that are pre-selected in here. We can change size, bold, italicize, underline. And there's 4 types of callouts. So we have a note, just text. That's what we've done here. An arrow. So now here we could point towards some kind of an observation, right? Like it looks like there was something at 55 megahertz, or what's going on with this distribution. We can add all of these notes in, and these save on screenshots. We can also, rather than just an arrow, we can draw a box. So let's grab that box, and let's say, we're interested in whatever's going on right here. So pretty easy to move this around and configure exactly where we want that box to be. Or a bookmark. Bookmark is really cool because you can set this X position in seconds. So however far before or after the trigger that you're interested in, and it's going to measure what that amplitude is at that point, right? So you see it automatically updating, and this works for currents, voltages, whatever it is that you're measuring. This will continuously read out that exact value. We also have cursors, right? Cursors have been a thing for a long time on oscilloscopes. These are incredibly easy to use. A right click and you can get into the advanced options, like do you want these to be waveform, vertical bars, horizontal, vertical and horizontal, and we can configure them in here to be, maybe that you want them linked, right? So when you move the A, the B goes along with it, right? And you can gate measurements, say let's move it over onto our, let's put cursors over here now. And let's get back into that configure cursors. And let's say that we want these to be linked. And I can go into this measurement, and let's say I only want to measure the frequency in between these cursors. That's something we can do with a feature called gating. So gating, we can gate by the screen. Let's say we were to zoom in. We could gate on cursors, logic, a search, or time. And we're going to pick based on cursors. So you see that when I changed my settings, the histogram restarted drawing. And now I'm only making measurements on the frequency in between these cursors, and we can move them around. And this is really nice when you have a really nice long acquisition and you only want to interrogate one specific part of it. All right, that is a pretty good, very quick overview of the user interface. Let's jump back over to the slides now. Okay, that was a very general overview of the 5 Series B MSO. Right, that could apply to any of these applications that you see here on the screen or more, right? Any way that you're using the oscilloscope, you need to know how to manage channels, measurements, use cursors. Now we're going to focus in. And the first one we're going to focus in on is embedded systems, right? This is bringing up a board where there's a multidisciplinary team. You're working on bringing up a bunch of different components, most likely. Some serial communications are going on. Chips are communicating back and forth. We are going to start with showing the serial bus decode features, search capabilities, triggering capabilities, serial bus decode table, and then we'll touch on spectrum view. Spectrum view is one of my favorite features in the 5 Series B MSO, and it is very fun to show. Let's jump on into the scope. Okay, I've done a default setup on the oscilloscope. I know that I have set up some very interesting signals on channels 5 and 6, so I'm going to move the trigger over to channel 5, and we're going to do an auto set. The oscilloscope is now going to optimize my vertical and horizontal settings, and let's go ahead and open up this horizontal scale. There we go. So serial communication, it looks like here. And it looks like we've got some noise on our signals, right? So let's go ahead and set up maybe a bandwidth limit at 20 megahertz so we can get a better view of the ones and the zeros without all the noise. Okay, and I'm going to use a feature here called visual trigger, where I'm going to draw a box, and I'm going to say that I want the waveforms to be out. I don't ever want to trigger when there's a waveform inside this box, and that really helps me get a good start here. We could also use a hold off, right? We'd go into trigger, we would set the mode in the hold off, and we'd set this for some kind of a time, like maybe 300 microseconds. Another way to do that. Okay, now I'm going to add a new bus. We're going to click down here. We have the clock on channel 5, the data on channel 6. Let's take this threshold, and I'm looking, and it looks like 2 volts will be an adequate level for the threshold. And for the data, it looks like 2 is going to be good again. You see this blue line to show up and confirm exactly where that is. And now we're getting these hexagons, red and green vertical lines. And I'm curious what those mean. So let's go ahead and stop the acquisition. We will zoom in. And it looks like we're getting readouts, right? So we see an address 50H read, data 12H. This green here is the start of the packet. And this red here, when I click on it, it shows me that it's the stop of the packet. And we can now interrogate all of these and see exactly what's going on inside of this serial bus decode. Now, I2C was initially selected for us, but we've got lots of different options in here, whether you're working with something automotive like CAN, LIN, FlexRay, something that's more aerospace and defense related, like let's see, this mil standard, AirInc 429, SpaceWire, or more power related, or NRZ, non-return to zero style. Lots of different options in here, and we're continuing to develop and release more serial bus standards. We can really set this up depending on what our embedded system is doing. So we can show both the bus and the waveforms down here. So you can see now the clock and the data shows up if you want to see those together, and we can show this either in hex or in binary. And then we can set the label, like maybe this is I2C and it's our microcontroller, right? And I push enter, and that now shows up right here in this bus decode, and we can move that around. Click tap on the minus and the plus actually can hide or show the waveforms. Now, another way that I like to look at this, let's go ahead and open this up so you can see the full vertical, is taking the clock, taking the data, and taking the decode and putting everything together. You see how we have it right now on 3 separate slices? Let's go ahead and combine those. So I'm going to take this channel 6 badge, and I'm going to drop it on top of channel 5. And what you see here is now the clock and the data have become overlaid on top of each other. And I can do the same thing with this bus, right? I've taken the bus and I drop it right on top. Now, when we zoom in, it's incredibly easy to tell exactly what's going on because my eyes are only looking in one area, right? I'm not looking at the top wedge, the middle wedge, and the bottom wedge. That was a quick intro into the serial bus decode. Now let's go this data 18H. Let's zoom all the way out, and then let's go try to find that and see if that happens anywhere else. To do that, we're going to open up a search. We're going to search for a bus, and let's go ahead and search for the data 18. Where did we find an 18? There it is, right? We see this pink triangle here. It is showing that in the whole acquisition, it was found one time. It starts right here and it ends right here. And I can now click this right arrow, and it's going to toggle me through all of those one occurrences. And boom, the zoom window shows right up exactly where that is. So let's say that we had a longer acquisition. All right, let's do that. Let's we opened up our horizontal settings. So now this is 1.25 million point record length. I'm still doing that search for that 18H, and it now shows up 37 times. So let's click through those and go ahead and zoom in. So here's one at about, 220 milliseconds after the trigger, another one about 210, another at 200. So it looks like maybe this is happening every 10 milliseconds. Pretty cool. We can see the pink triangles exactly where that shows up. This search capability, it works for really any of the trigger types. And once we have a search set up, let's turn off search 2. Here we can copy the search settings to trigger, or we could do the opposite. We could copy the trigger settings over to search. But let's where we're triggering on 1.91 volts. Let's copy search settings to trigger, and now we're going to trigger on I2C data being 18H. And now when we, let's go ahead and stop that. Well, and when we turn off our zoom, we're going to really open up our horizontal settings. So we're really tight in. Now we have a really stable trigger event on that 18H, right? Let's, maybe I zoomed too far because we need that whole packet, right, to be able to decode. There we go, 18H every single time. So we've been able to identify this exact packet and see what is going on with that. Tables is going to be the next thing. So over here we have results table. We can add measurements, search, bus decode, peak markers, or harmonics for frequency response analysis. You guessed it, we're doing bus decode. And you can see the start time. We can right click here and we can double click. We can configure the table and we can add things like stop time, unknowns, ACKs, and it is decoding one packet, right? Index one, what is it that's the address and what's the data? Let's change the horizontal settings again so we get multiple packets. And now this bus decode table is really lively as it is sharing all of the information for all of these packets. A quick right click and we can save this table out as a CSV. Or we can save this whole thing as what's called a session file. Right here, a session. And we can take this over to another oscilloscope or over to a PC, and we can analyze the data in this session file that we've saved off somewhere else, like on a PC. We'll really show that towards the end of this session today. Now, that really covers the serial bus decode, search, trigger, tables. I'm going to do a default setup, and we're going to look at something called spectrum view. Again, anytime that you used to use an FFT, you can replace it with this awesome spectrum view feature. So I'm going to add a measurement to learn about what this signal is. This is a 40 megahertz clock, right? Very repeatable, very nice and clean. Let's see exactly how nice and clean that is. So in the channel 1 badge, I'm going to open up spectrum view and turn that on. The top half kind of looks like a spectrum analyzer or what you would see from an FFT. Let's do that. Let's add an FFT. If you're really comfortable with FFTs and you love them, we have not taken that capability away. You can see the FFT here in spectrum view here. The FFT goes from DC up to 1 gigahertz. In spectrum view, it looks like is right now set up to go from 750 megahertz to 1.25 gigahertz. Let's get those both set up around this 40 megahertz clock. So I'm going to double tap this spectrum view badge down here. I'm going to put my center frequency at 40 megahertz. Enter. And the span, let's zoom in so we can get something nice and clean. It looks like there's some kind of a glitch on this clock. Interesting. So this now goes from 39.5 to 40.5. So a double click in here. Let's not auto scale. Let's say that we want that to go from 39.5 megahertz to 40.5 megahertz. So we now have the same thing on spectrum view in the top right as we do on our FFT in the top left. Now, spectrum view is showing me this nice clean signal. The FFT is just showing me a flat line, right? I don't have enough cycles in here to resolve the frequencies. Said another way, our resolution bandwidth is really limited right now in the FFT. So let's go into the horizontal settings. I said that I needed more cycles, right? And as I click more cycles here, you can see our FFT is getting a little bit better in quality. And now it looks like we've got about the same thing on our right and on our left. The problem with that is to get that really great quality, I now can't look at the individual clock cycles, right? I've lost the ability to view both what's happening in the RF domain and the time domain at the same time. And you notice the whole time I did those changes, spectrum view stayed exactly looking exactly the same, right? So let's zoom back in so we look at just 1 or 2 cycles. And again, Spectrum view is still showing me exactly what's going on in the RF domain, and I've lost the FFT. So there's this really complicated, not complicated, but just it. You got to really plan out your sample rate, your record length, and what frequencies you're trying to look at to get a good view in FFT. You don't need to do that with spectrum view. It just works. Again, you can focus on what you're working on and not on your test and measurement settings. Now, we're getting that little glitch that we were talking about, right? So let's spend just a moment looking at one of the advanced spectrum view features, which is let's do a frequency versus time. And so now what this is showing is the time of this view and this view are perfectly correlated together. So what's happening right here is what's happening right here. The amplitude is deviation from center frequency. So when we have a perfect clock, we deviate 0 hertz from center frequency. That's this nice 40 megahertz tone. And I can actually hardware trigger on this. So now you see that I've set up a hardware trigger, and I'm looking for something where we move away from that center frequency. And let's take this and open up our, let's get more cycles. And in our trigger, I only want to trigger when my trigger condition is met. So that's going to be a normal trigger. And look at that. It looks like we're getting some kind of a deviation where the clock dips low and high, and you can actually see that exact behavior here in the analog view. So let's grab some more cycles. And you see this yellow rectangle here has it changes size as I change, right? So it becomes a smaller percentage of our record as I grow, and it's a fixed time distance. Let's stop the trigger. What this is this is called spectrum time. This is the start and this is the stop of where our spectrum view spectrum is being calculated from. So as I move it around, right here is where we had that clock jitter, or that clock dip below, right? It looks like it dips around 200 kilohertz below center frequency. But here I don't have that. So I have a nice, good, neat tone here. And then I get to my trigger condition, and that's where we start to see the clock have its issues, where it goes a couple hundred kilohertz below 40 megahertz. And it looks like it happens over here again about 8 milliseconds later. Let's drag spectrum time over there, and the same behavior happens a second time. I'm not going to do the full demo, but you can set this up on 8 channels. You can have 8 independent selections for where spectrum view is, and you can have 8 different center frequencies. You can set up all sorts of different mixed domain analysis, and this pairs really well along with that serial decode that we were doing, right? If you have chip-to-chip communications that you think are causing issues on a power rail, you might want to turn on some kind of a view of the spectrum so that you can correlate this serial communication pattern with this kind of a clock issue, ripple on your power rails. Maybe it's an EMI emission, right? You could use a near field probe and you could be sniffing around on a board or around your enclosure, and you can be now correlating things from many different channels to what's happening in your spectrum. And you get to pick your record length, sample rate, all of the horizontal settings, and know that spectrum view is going to be there looking at the signal exactly how you want it, and you don't need to make the trade-offs like we used to on FFTs. That was fun. That's one of my favorite demos to do. Now let's get back over to the slides. So again, here's the applications that we're talking about. Let's next go over to silicon carbide and gallium nitride and switching analysis. We're going to look at double pulse test. We're going to look at silicon carbide and gallium nitride. I'll mention a few things about the Tektronix AFG 31000 and a new software feature that we just launched. This X stands for 4, 5, or 6. So a 4 wideband gap double pulse test, 5 wideband gap double pulse test, or 6 wideband gap double pulse test. This is the new software application to completely simplify doing double pulse test on switching devices. Now back over into the scope, we're going to open up a demo here. And in this demo, let's go over to wide bandgap double pulse test measurements. So this was recently launched. What this software helps you do is when we go into measurements, we now have this wide bandgap double pulse test tab. And you can pick what kind of power device you have if you're doing something with a MOSFET or an IGBT. And then you select your voltage, your current, your gate source. And then really quickly, you can then add an E-on measurement, E-off, peak voltage, peak current. And you can see here, right, we have VDS, ID, and VGS. And then the oscilloscope will automatically, when you set your voltage, your current, and your gate sources, the oscilloscope will automatically calculate the E-on power and it will plot that for you. And you can see how that power is changing as a function of time. There's also a switching timing analysis. So the first one is switching parameters. Now in switching timing, T-on, T-off, TR, TF. Again, all you have to do here is set what your voltage source is, drain, what your current source is, and what your gate source is, and you get all of these automatically set up for you, and diode recovery analysis. So you saw here, there's different inputs now. You just need your current and your gate, and you get your TRR, your QRR, and your ERR, right? So here you can really do reverse recovery, energy. Automatically, the scope does all of this and sets it all up for you, and this is going to really radically simplify doing double pulse test. You have to click less buttons. You have to think less about, okay, which one is my current probe? I need to do this kind of math over there. It helps by really clearly helping you label, right? So you can see VDS, ID, VGS. It does the plotting of power. And when you come back with whatever your next design is, you click the same buttons and it does this automatically for you. So it is really going to simplify the way that you can characterize your traditional silicon or your wide bandgap materials. Next, with silicon carbide and gallium nitride, our probe recommendation is the IsoView probe. This has got an incredible, it's optically isolated first off, which enables an incredibly high common mode rejection ratio. This helps you look at ringing, and you can really trust that what you're measuring isn't a function of a differential probe, right? The probe gets out of the way so you can actually see what's happening on your within your switching devices. This has been a complete game changer because, I'll quote a customer here. I was never able to see this before. I didn't know this is what was happening in my circuit. That was at an industrial customer that was working on the design of some really, really high current and high voltage signals inside of a generator. Next, like I said, I'm going to touch on the AFG 31000 really quickly. This is a Tektronix 2-channel function generator, and inside that function generator, the team has designed a user interface where you can set up multi-pulse test. And so what you do is you set your amplitude of the first pulse, amplitude of the second pulse, duration of the first pulse, duration of the second, that gap in between, and that helps in just a couple of clicks you set up a double pulse test. So you have your DC power supply supplying tens of volts to your board. You have your gate driver being the AFG 31000. It's sending a couple of pulses through to whatever your MOSFET or your silicon carbide is. And now you have the oscilloscope with this wide bandgap double pulse test software doing the analysis. So a full solution when you look at the power supplies, the function generator, and the oscilloscope to do the analysis on. Let's go over to the slides really quick. And we can see here, these are the IsoView probes, right? So we were talking about the common mode rejection ratio of the optically isolated probes with plus or minus 60 kilovolts at 100 volts per nanosecond or faster. And this MMCX connector, if you can put some of those on your board, that's going to be the best signal fidelity with a really great ground connection. Now let's move away from switching devices and silicon carbide and gallium nitride over to converters, inverters, motors, and drives. So this could be Anything three-phase related is what we're going to focus on here for the next few minutes, whether that's BLDC motors, multi-phase inverters and converters. And we're going to first look at a view of the setup. We'll do a quick introductory to phasor diagrams, and I've got a quick video on the DQ0 functionality for direct quadrature analysis. So this might look something like your really high-level schematic, right? You've got your three-phase AC line drive inputs. You have some kind of a variable frequency motor drive where you've got all of this complexity going on, and then at the end you have your motor and your mechanical load. And when you're using something like a power analyzer, you get to know how the whole system is working, right? You get the summary kind of your efficiency and what your power is looking like. What doing three-phase analysis or inverter motor drive analysis on an oscilloscope gives you is you can look at every single sample point, and you can correlate, right, in this with serial decodes. You can correlate what's happening in your inverter or your rectifier, your motor, with the other signals inside of your oscilloscope and how things are functioning over time, like at the startup of a motor. What's happening at the startup of a motor? It'd be really hard to see that on a power analyzer. So we can do digital probing for sensor signals, like magnetic sensors, start and stop profiling, multi-analysis capabilities, like we were just looking at the spectrum view a few minutes ago. Maybe you have some kind of an RF analysis you want to do, correlate something in the spectrum. We can look at time trend. The phasor diagram I'll show you next. What's happening inside of your switching? How is the silicon carbide in the inverter? How is that impacting things at the motor's end? We're going to look at ripple. Maybe you've got some DC power supplies that are helping power this three-phase, and you with the communication side, and you got to correlate things on DC ripple, harmonics, where we can see if we're pass or failing limits, magnetics, and we'll do a quick video on DQ0 as well. So what does this look like? Typically, it looks like your MSO 58 with three differential probes. You can see channel 1, 3, and 5 have these differential probes here. TMDP, THDP. I didn't mean to have that progress. Connected in, we've got this board with a BLDC motor. 3 current probes here. 1, 2, 3. We're looking at the three-phase power to the BLDC motor, and maybe some power rail probes as we're trying to interrogate what's happening on our 33-volt power rail. This is a view of the phasor diagram. You can see here you've got your 3 currents and your 3 voltages. And you can set up with line to line, or you can mathematically convert over to a line to neutral mode, depending on which way you like to view this. And now a view of the phasor diagram. So let's start by pausing this. There's a lot going on the screen, so I'll introduce everything that's going on, and then we'll watch the video. Here's our phasor diagram. So this is your current, VA to neutral, VB to neutral, VC to neutral. You have your D and your Q vectors, and what is being, this purple circle is the resultant, right? So it's the sum of the squares of the D and the Q give you this resultant. Where's this being calculated from? So you can see we have marker 1 right here and marker 2, or marker 1A right here and marker 1B right here, and you're going to watch this mouse moving marker A around, and the resultant is being calculated as we move the marker 1 around as this measurement is gated. This is using the IMDA software with DQ0, and let's watch the video. So as the cursor is being moved, you can see this resultant moving around as the D and the Q, which are 90 degrees out of phase, moved around. The idea here is, again, one instrument, the 5 Series B MSO, to replace really complicated setups or give you analysis that you maybe never would have been able to get budget to buy multiple instruments, multiple setups, multiple bench space requests. Now we're going to get over to another slide similar to the first one that we looked at for inverter motor drive testing, but what is the full test solution? Right, so it's the oscilloscope, It's probes and software that help you connect to the right signals with high signal fidelity and then do the analysis either live on the oscilloscope, like shown in the picture in the middle, or on a PC using Tekscope. Here we've got a picture of that isolated ISOView probe with the optically isolated signal, where the probe is optically isolated from the signal and high common mode rejection ratio. And next, let's do a quick summary on remote calibration. So in the oscilloscope, let's jump over to the oscilloscope. We can go File, Utilities, and Mount. What this does, we can mount to a network drive or to tech drive. Tech drive, think OneDrive, Dropbox, cloud storage. So I'm going to click tech drive. We're going to name that tech drive 1. Can put whatever we want in there and say connect to tech drive. And what shows up is a QRC. I'm going to now pull out my phone. See my phone here. Turn on my camera. I'm pointing it right there at that QRC, and I get a pop-up. It's taking me to Tech Cloud, where I will log in with my login. I have now been given an activation code, so this is confirming that what I see on my phone matches what's shown there. So I see PKNHQL. That matches on the scope. Let's go next. I agree to let these two things connect together, and I'm done now. You can see activation successful. So we can now mount tech drive. Now you see here in the drives, next to C, I now have tech drive and my files. So you can see on my scope, I've now got all these files that were previously saved to my tech drive account. So I can take things from the cloud down to my scope now, right? That's what I've got right here is I'd be able to file, recall a session. And where do I want to recall that session from? You guessed it, I want to recall that from tech drive. So let's say it's in my files, and we'll pull down. Let's look at, I don't know, VDS VGS 100 millimeter. And I've now downloaded this double pulse test we were running from the cloud onto my oscilloscope, which I'm remotely connected to, and we can do all sorts of measurements on this static waveform. I can go the other way, right? I can save as a session. I can browse. Let's get off of C and onto tech drive. I can now take this that's on my computer and I can save it up to tech drive. I can share with colleagues. I can download files from colleagues. That's this shared with me folder, is people can save their files out into mine. So they're in another country, they're in another lab, they're at their home. You saw me set it up. It's super easy to connect tech drive to your scope, and within minutes you are now storing things to the cloud. A great functionality that pairs with that is what we call Tekscope. That is a PC-based application. So now we're in Tekscope, and we can do the same thing, right? We can recall files down from tech drive, off of a thumb drive, and I am no longer looking at an oscilloscope. What's on the screen is on my PC. It has nothing to do with the oscilloscope hardware. So you could have somebody in the lab, like a technician or one of your hardware engineers, probing, collecting data, saving things up to Tech Cloud, and you could have tens or dozens or hundreds of engineers on the other end pulling things down from the cloud, wherever they are in the world, and analyzing and doing analysis and creating reports based on that data. So now you have your oscilloscope, which is that really complicated hardware required to take signals and accurately collect the data. You have Tech Drive to connect that oscilloscope to the cloud. And then you have Tekscope, so you can then pull the information down from the cloud and do analysis and debug anywhere. This drives just like the scope. Everything that we were doing, right? Drag and drop, add a measurement. I can turn channels off. I would be able to pull in references, and using this Tekscope, I can pull together dozens of signals. So you're no longer limited to 8 inputs, but many more, 16, 32, and you can do more complicated analysis. You just need to think about how you trigger those multiple instruments, and when you pull them back into Tekscope, then how to align them in time. Tekscope, I love it. It's been really helpful with COVID, with remote work, hybrid work, and then traveling, demoing, collaborating with customers when they run into problems. So, in closing, we wanted to do a quick refresher. What did we talk about? We talked about your applications. We talked about the 5 Series B MSO. We talked about briefly touched on the probes, right? 25 years of probing innovation so that there's a current probe, a differential probe, or an optically isolated probe that's been optimized for your application and your measurements. And we spent a lot of time talking about software solutions, things that Tektronix has invested in to make your analysis easier to do the first time and more repeatable, less prone to user error when things get set up incorrectly, whether that's an intern that's come on, a technician, or somebody that's really busy and wants their oscilloscope analysis set up right away. And repair calibration. Again, we're the ones who designed this instrument. We understand how it works inside and out. Trust us with doing the repairs and calibrating when needed. We'll spend one quick second on this slide. We also have these software bundles that we've come out with, and we're always adding to them, and we're always releasing new functionality. So you can see here this starter bundle. This comes with the arbitrary function generator. It comes with decoding of I2C, SPI, RS-232 UART, and you can get this for 1 year. Maybe you're a little bit wary of this software. You can try it out for a year, or you can buy the perpetual license. These pro bundles really focused in on some of those applications we talked about. Serial decode. This is one piece of software that unlocks all of the serial decoders that we have created. Power. All of the power solutions that we've launched. So you'd see the wide bandgap double pulse test get added to this here once we launch it. Signal integrity, compliance, automotive, MilGov, and all of these pro bundles, whichever one you select, they also come with everything that was in the starter bundle, the AFG, some of the decoding, and double your record length, 225 million points. And then the ultimate bundle. That includes the starter bundle, it includes all of the pro bundles, and it also includes some of our advanced spectrum view functionality, like the RF first time, video triggers, and the maximum record length of 500 megapoints, which is more than 8 times, which is 8 times larger than the standard record length. So that's the way that you can really quickly make a purchasing decision and make sure that you're covered in all of the software capabilities that you need. We covered a lot in this demo, so I would not be surprised if you had questions. Please feel free, again, to drop those questions in the chat, and our team is going to reach out to you and get back to you and help answer that question. I so appreciate you taking the time to attend this webinar, and I really hope that you're having a great day and that we can connect soon.